Good morning. I'm Bonnie Gardner, co-chair of the Public Affairs Forum of the First Unitarian Universalist Church. The forum is free and open to the public. To find out more about our forum presentations, you can go to our website at www.austinuu.org. And now Michael Laberkian is going to introduce our forum speaker for today, Dr. Steven Finkelstein. Thank you, Michael.
Thank you very much. The recent upgrade of the Hubble Space Telescope has opened a new window on the distant universe. Over the past years, he has been able to discover the most distant galaxies ever. Dr. Finkelstein will discuss how we identify these most distant galaxies and what their nature tells us about the galaxies, how they form and evolve. So it's all about creation. It's all about the force of creation, which keeps creating and keeps evolving. He will also discuss the HETDEX, H-E-T-D-E-X project, which uses distant galaxies to probe the nature of dark energy. I wonder about dark energy because it seems to be in the politics of our country, right? A lot of dark energy there. Now, Steven Finkelstein is a Hubble Fellow in the Astronomy Department at UT Austin. Lives in Austin with his wife Keely, who is also an astronomer at UT, and their young son. Now, in the question and answer, there are never bad questions. Don't be intimidated by this intellectual subject. There are never bad questions. But he will always give us a good answer no matter what your question. You can ask him about eternal life and science fiction and space people. But he's a real explorer of the future and the universe in the spirit of Christopher Columbus and Leif Erikson. I present to you Professor Finkelstein.
Thank you, Mike. Everybody can hear me okay? Yes. Thank you. So I'm actually not yet a professor. I hate to disappoint you. So, thank you very much. So my position is actually, the title is a Hubble Fellow, but that's a fancy word for something called a postdoctoral researcher. And what that means is, in the field of astronomy and most sciences, you go to, undergraduate for 4 years, and then you go to graduate school for anywhere from 4 to 15 years, depending on your field. It was 5 years for me, and then you have to do something called a postdoc, which is basically, after you get your degree, you go and just do research for, they usually last about 3 years. In astronomy, you typically have to do 2 of them, so I'm now in my 4th year as a postdoctoral researcher. And then after that, then you apply somewhere and hope somebody hires you to be a professor. So I'm now close to that stage of my life. I was actually at Texas A&M for 3 years. Don't tell anybody if you're a Longhorn fan. That was where I did my first postdoc, and I just moved here to Austin 6 months ago. And I love the city so far. So I'm very happy to be here. My research centers around looking for the most distant galaxies we can see. And so not everybody knows what a galaxy is. So just a brief definition of a galaxy. You've probably heard of the Milky Way galaxy. That is a galaxy that we live in. Our, of course, Earth, our star, all the stars around us, live in something called the Milky Way galaxy. To get a little sciencey on it, it's a gravitationally bound system of stars. So it means the sun can't just go on and escape. We're orbiting the center of the Milky Way due to gravity. There's many other stars, hundreds of billions of stars in our galaxy. There's lots of gas in our galaxy. There's a huge black hole at the middle of our galaxy. And we're all part of one galaxy, the Milky Way galaxy. Kind of an average galaxy, what we see. It's pretty big, but I would call it average. So what we want to do is go look for other systems like the Milky Way. And in fact, we don't have to go too far. Orbiting our own Milky Way are these 2 galaxies called the Small and Large Magellanic Clouds. Unfortunately, in the northern hemisphere, we can't see them. But if you ever find yourself in the southern hemisphere and look up into the sky and see these 2 kind of cloudy patches, those are actually other galaxies. They're pretty close by, but they are distinctly separate from our own, but they're close enough that they actually orbit our own galaxy. We go a little bit further away. There's something called the Andromeda Galaxy that I'll show you. Actually looks a lot like our own galaxy. And here, let's go to some of the first pictures I have to show you. When we talk about galaxies in the local universe, and so I have a very broad term, a broad meaning when I say local. I mean galaxies we can see nearby. Some of them you can even see with your naked eye. Maybe some you need binoculars to see. We like to classify them by how they look. Of course, it seems a logical thing to do, right? So they usually fall in 3 categories. Spiral galaxies seems pretty obvious. You look at them and you see a spiral shape. That's what we think the Milky Way looks like. Although, as you might imagine, it's actually very hard to see what the Milky Way looks like because we live in it. We can't get above the Milky Way and look down and see what it looks like, so we have to make inferences. But the galaxy Andromeda, I mentioned, is a spiral. There are elliptical galaxies, which are very different. They are basically these big, round balls of stars buzzing around in all these random directions, kind of like a hive of bees. And then there are irregular galaxies, which look irregular. They kind of don't fall into one or the other. So this was actually one of the many things that made Hubble famous. So Edwin Hubble was an astronomer, and I think most of his interesting results came out in the 1920s. This was his classification scheme. So he looked at the galaxies in the sky, and he came up with this thing we call the Hubble tuning fork diagram, because it looks like a tuning fork. So the elliptical galaxies look like this, these kind of little round balls here. Elliptical zeros are perfectly round, and elliptical sevens, or E7s, are very elongated. So the more elongated you are, the higher this number is. And then spirals, if you have a bar in the middle, you can kind of see it here, like that. You fall on this end. If you don't have a bar, you fall on that end. And the SA, SB, SC just tells you how tightly are the spiral arms bound around you. You can see the SAs are pretty tightly, the SCs have more loose flowing spiral arms. So these are galaxies. We can look at some more recent realistic images of galaxies. These are images, actually infrared images, so light just redder than your eye can see. There's a telescope in space that's purely dedicated to looking at these. It's been up there for, I think, 8 years now, called the Spitzer Space Telescope. And this is actually the Hubble diagram, but now with real galaxies. Elliptical galaxies here, kind of looks like these balls. And then over on the right side, you see all these spiral galaxies. And again, these are all what we would call local galaxies, very nearby. Only galaxies that are very nearby can we see them in such detail to get these excellent pictures of them. So when we look at these galaxies, one thing we can do, of course we can study how they look, and that's what we've done to say, okay, you're an elliptical or you're a spiral. But then how do we find out what is going on in these galaxies? What kinds of stars are in these galaxies? Are more stars currently being born? Are there no stars being born? That's kind of one of the basic things we can investigate when we look at a galaxy. We call it the star formation rate. How many stars are formed per year? When we look at elliptical galaxies, they appear very, very red to the eye. And what that tells us is there's not a lot of stars forming, because when stars form, galaxies tend to look blue. So ellipticals are red, spirals tend to be blue, irregulars also tend to be blue, so that kind of tells us physically what's going on. Through some reason in their past, ellipticals are no longer forming stars, spirals and irregulars are still forming stars. That already gives us a clue into what's going on with these galaxies and how they're kind of living their lives. So a natural question to ask, or at least what I think is a natural question to ask, and which has led me into my line of research is, okay, we know what galaxies look like now, but what did they look like in the early universe? Now, an estimate of the age of the universe is also an evolving thing. As we come up with better and better experiments and learn more and more, this number changes, but we're kind of tightening in on a pretty exact number on, we think the universe formed about 13.6, 13.7 billion years ago. So that's a long, long time for galaxies to change. But what's great about the universe is that there are these laws of physics in the universe, and one of them is that light has a finite speed, called the speed of light. We're not very original with our names. So that means that the farther away you look, you're essentially looking back in time. So for example, the sun is, we call it 8 light minutes away. So that means when you look at the sun, well, don't look at the sun, but if you were to look at the sun with a solar filter in your telescope or something, the light you're seeing left the sun 8 minutes ago, and it was just traveling through space all that time to get here. So 8 minutes doesn't seem like a lot, but the sun is relatively close. So when we go look at galaxies in the sky, for example, those Magellanic Clouds are a few 100,000 light years away. So if you were to go to the southern hemisphere on a nice trip, you see the Large Magellanic Cloud, you were seeing as it was 200,000 years ago, which is a lot, right? So that's great, so we can study that galaxy. We know how it was a little while ago, but let's go look at the early universe, and if we can find galaxies 5, 10 billion years away from us, we're seeing them as they were 5 or 10 billion years ago. And because we know the Milky Way, and galaxies like our Milky Way, only had about 13 billion years to form, you might expect, as you look 10 billion years into the past, things look very, very different. And in fact, that's what we find. So I'll do one slide here on the formation of the first galaxies. This is all theory. These are what people, they sit there, they look at their computers, they run these models, they make these cool movies that are playing right now. This one on the top is a movie of the density of gas in the universe. So on their computer, they make a big box, they throw a bunch of gas particles in there, and they just let them interact due to gravity. And you see that they start to collapse along these filaments. So things that are red are more dense. What you see on the bottom here, these are where the stars are. Actually, we'll start this over again, and then we kind of know what it is. Okay, hopefully that will play. So on the bottom, we see where the stars are, and as you can see, you'll start to see the densest regions here and here, and that's where the first stars will form. There's one going off right there. I don't know if you can see it. I can see it coming right up here. So you'll start to see stars forming there. So how do these guys at their computers know that this is what's happening? Well, we've made a lot of observations that have led us to believe that the universe formed in something called a Big Bang, some big explosion about 13.7 billion years ago, and that was really, really hot. And so for a while, nothing happened because it was so hot. But after the explosion, the universe continued to expand, and all the stuff in that universe cooled, and what happened is that matter in the universe, and so when I talk about matter, I'm actually talking about dark matter, which I can talk more about maybe in the question session. We don't have a ton of time to talk about it. But we have evidence that there exists a form of matter called dark matter that we can't see with our eyes, but it interacts with us and everything gravitationally. That starts to collapse along these filaments here. Once that collapses, that draws in all you can call it the real matter, the matter we know of, hydrogen atoms, helium atoms, things like that. They fall in here. Once the universe expands a little bit more, those hydrogen atoms can start to form these gas clouds. Those gas clouds collapse and form stars. And that's what's going on here. So in these really dense regions, we start to get stars forming. And so what happens is, first, maybe you just have a single star forming, but in these dense regions, you've got a lot of gas, and these are essentially where the first galaxies are forming in the universe. So we can make these movies because we think we understand at least when the Big Bang was, kind of the conditions around the time of the Big Bang, and we think we understand how gravity works. Knowing just those few things, we can make these movies. And so that's what the theorists have done. There are many, many astronomers who devote all their research to this theory, and then it's up to us observers to go try and observe as far away as we can and see how our observations match their theories. If they don't, then we go back to them and then we say, hey, you got to change your models. This is what we see. And then they change the models, come back to us, we make more observations, and we just kind of go back and forth, back and forth. But what theory tells us is that these first galaxies that are forming in the universe must have been forming stars at a crazy, crazy rate. Very, very high star formation rate. For example, the Milky Way that we live in, our galaxy forms stars at a rate of, we would say, 1 solar mass per year. So that means on average it's making a star like the sun once per year. Or maybe it makes 2 stars half as big as the sun once per year. Or maybe a star twice as big as the sun every other year. So on and so forth. So we want to know, what do those galaxies look like? So one thing we could do is just go out and try and find galaxies that are forming stars at a really, really big rate. That's tricky because we know what star formation looks like in our galaxy, but how do we know what star formation looks like in the distant universe? This is a very famous picture that was taken by the Hubble Space Telescope, I think around the mid-1990s. This is actually dubbed the Pillars of Creation by the media. And what this is a very zoomed-in view on a region of forming stars in our galaxy. This column here is a column of gas and dust, and each of these little squares here are where young stars are forming. This is actually, Mike mentioned my wife is an astronomer. This is actually one of the images that she used. Actually, the next one is one she used in her thesis work. So we can see where stars are forming. So, okay, we could just go out, look in space, look for things like that. But we zoom in a little bit, or zoom out a little bit, sorry. We see that those pillars are just one part of this giant region. So this is a region called the Eagle Nebula. It's a star formation region in our galaxy. This is an image actually taken with the Spitzer Space Telescope in the infrared, and these squares again show you where all the little stars are forming. This is actually the image that my wife worked on. This image is maybe 4 or 5 years old. Okay, so we could go look for this, but again, this is still zoomed in very far. So where does that live in the galaxy? That's just a tiny speck out in a random place in the galaxy. This is actually an image of another spiral galaxy, but we think that our galaxy looks something like this. Okay, so it's blue. Remember I said blue means forming stars. It's got those regions in there. Let's go look for these. But if you take this galaxy and throw it way in the distant universe, you want to know what it looks like with Hubble, it looks like this. So that's a little bit harder to identify. This is actually an image from my thesis. This is a galaxy that was from about 1.5 billion years after the Big Bang, and I'll talk about that in a little bit. So this is a very distant galaxy, so that's cool. It certainly looks a lot different from the Milky Way, but it's really hard to tell because instead of having these glorious big images, we've got, I don't know, maybe 10 pixels here to work with. So there's a lot to do. All right, so I said that. All right, so instead of trying to identify them by just saying, what does this galaxy look like to the eye, we would call that morphology. We can look for some other signposts of star formation. So after the Big Bang, once gas is kind of formed in the universe, there was only hydrogen and a little bit of helium. So we can kind of work with that and say, okay, if you have hydrogen and it collapses, it's going to form stars, what will that look like? So I'll do a little bit of physics here. We'll talk about the atom. We'll just talk about hydrogen because it's the simplest atom. It's got one proton and one electron orbiting around it. So the funny thing about electrons is that they only want to have certain levels of energy. So if you're an electron and you're orbiting around the hydrogen atom, this is an energy diagram. If you're on the bottom here, you're happy, you're not going anywhere. But something happens. Maybe you collide with another atom, maybe you absorb a photon, a little bit of light, you get excited. You're up here now. You can't go here anywhere in between. You can only go up to here. Once you're up here, you have nowhere else to go but back down. When you go back down, that's with this arrow here, you will emit a photon or light at a certain wavelength. By wavelength, I essentially mean color. So atoms can only emit light at certain colors. And that's really cool because that allows us to go take what we would call a spectrum. So we look at a galaxy with a telescope, we take the light and we disperse it. You can use a prism, or now we use gratings or some more advanced things. But you can then look for these spectral lines. You can say, hey, I know that. That's hydrogen. There's hydrogen in this galaxy. Okay? You can also be excited into this state. Once you're up here, you can go here, that way, and then back down that way, so on and so forth. So are there any number of things, just the simplest atom, a hydrogen atom can do. But as it turns out, this particular transition here, which we call H alpha for historical reasons, is the brightest one. And this happens to be visible by eye. It's in the red. If I was to have a hydrogen lamp up here and give you a little special set of glasses, you can actually see the spectral lines from that one. So let's just go take spectra of galaxies and look for this particular H alpha line. That's great. It's bright. We can see it with optical instrumentation, which is fantastic because we know how to do that the best. We can skip that. But there's a problem here. Something I haven't talked about yet. And it's something that, again, that we first learned from Edwin Hubble about 85 years ago, is that the universe is rapidly expanding. And that kind of throws us for a loop. Although, as it turns out, I think it's great that this is happening. This is actually a figure that Hubble published in the 1920s or 1930s, can't remember the exact year, and he was looking at galaxies, and he measured how fast are these galaxies moving away from us. If you didn't think the universe was expanding, you would think that maybe the galaxies are just all sitting and not moving, or maybe they're moving a little bit due to gravity. And so what he did is he measured how fast away they were moving versus their distance, and what he found is that as you go further and further away, the galaxies are moving farther and farther away from us in general. And this became something called Hubble's law. I know the distance to that galaxy, or conversely, I know how far away how fast that galaxy is receding from us. I can tell you how far away that is. That's fantastic. As it turns out, his slope for this relation was wrong by like a factor of 5 to 10, but that's okay. He was just starting. But the general concept is there. And so what's happening, this is a visualization of the expansion of the universe, is if you look at any galaxy in the sky, you will observe it as moving away from you. And that might lead you to think that our galaxy is particularly special. But actually that's not the case. If you were to go to any other galaxy, you would also see every galaxy moving away from you. And a good way to kind of visualize this is to think of ants on the surface of a balloon, or dots on the surface of a balloon. As you blow up that balloon, essentially more space is created between all of the dots on the balloon, all of the ants on the balloon, and they all appear as if they're moving away from each other. Similar to this little movie here of blocks, if you stand here at the center, you see everything moving away from you. But if you are this dot here, you also see everything moving away from you. So not only did Hubble see this, every single observation we now make kind of confirms this and backs this up. The universe is expanding, and because we think the universe formed in a big bang, a big explosion, it kind of makes sense. It's going to keep expanding up to a point. Does it expand forever? Does it stop and fall back? Well, we didn't know for a while. We do know now, and I'll talk about that at the end. So what does this mean for the light we see from galaxies? There's an interesting effect called the Doppler effect. And you may be more familiar with this with sound. For example, if you're driving and you drive and a train passes you, you hear the train pitch kind of increase as it comes towards you and then kind of decrease, go to a lower pitch as it goes away from you. And that has to do with the sound waves basically being more compressed as they reach your ear when the train is moving towards you, and they get less compressed as they move away from you. And that results in an increase in pitch and a decrease in pitch. Now the same thing actually happens with light, because just like sound is a wave, light is a wave. So if something is moving towards you, the light waves appear to become compressed and it actually looks bluer. We would call this a blue shift. If something moves away from you, the light waves get stretched out and it's called a red shift. Here's a good image here. This guy is here. He's moving this way. So everything over here appears blue shifted. He encounters the light waves more frequently. Everything over here appears red shifted. So light or siren, whichever you want to use. So what happens then in our expanding universe, when we go out and look at any galaxy, we don't see the light at the wavelength. So say we're looking for this H alpha line. We know the exact color, the exact wavelength it should be at. It doesn't appear there. It appears redder than it should be. And the farther away it is, the more red it appears due to the expansion of the universe. So astronomers call this number redshift. So if we were looking for H alpha at a particular wavelength, and it was actually at a wavelength double that, we would call that a redshift of 1. If it was a wavelength triple that, we would call that a redshift of 2, so on and so forth. The most distant galaxies that we know of today, or maybe a year ago or so, had a redshift of about 7. This number is kind of arbitrary the way we define it, but that kind of gives you a scale. We here are at redshift of 0. The most distant galaxies are at redshift of 7. And to kind of give you a scale, at a redshift of 7, when we're talking about galaxies there, the light that was emitted from those galaxies was from about 800 million years after the Big Bang. Now we're talking less than 10% the history of the universe, so there was much of the universe to go after those galaxies. So I wanted to go look for that H alpha emission line to go find these star-forming galaxies, but for galaxies with no redshift, that's great. We can take our regular telescope, even a small telescope, an optical spectrograph that we know how to build, and go find it. But once they're at a redshift greater than about 1, we can't do it anymore because this line has shifted redder than our eyes can see into what we call the near-infrared. Now we can build near-infrared cameras and near-infrared spectrographs to go look at this, but the night sky actually glows at these wavelengths. If your eye could see in the near-infrared and you went out, the night sky would be glowing even at night, right? So we can do it, but it's very tricky because all that light gets in the way of the light from the galaxy we want to see. So maybe this is not the best indicator to use, but there is another indicator, another line. I talked about this line first briefly. This one here called Lyman alpha, which in the local universe, so if you wanted to look for this from, say, the Large Magellanic Cloud, it's way in the ultraviolet. Your eye can't see it, and not only that, the atmosphere of the Earth actually blocks this line from making it to the ground. So if you want to look at this wavelength, you need to build a space telescope, which of course we have, or you could just look for it in galaxies that are distant and have been redshifted. So this line now gets shifted from the ultraviolet into the optical, where now we can see it with our eyes or with our ground-based spectrographs. What's also interesting about that line is it's been actually suggested as a great probe. 40 years ago in the literature, before we had anywhere near the technology to see it, a paper was written saying, hey, to find these distant galaxies, you should go look for this line. And so people actually tried to do that 40 years ago. As it turns out, they couldn't do it because their telescopes weren't big enough. But about 10 years ago, a combination of bigger and bigger telescopes and bigger cameras allowed us to find these galaxies with what we call the Lyman alpha emission. Okay, so we now call these Lyman alpha galaxies because we are not good and making up good names for things. But what's cool about these galaxies is they all have this really strong emission, and that tells us there's lots and lots of star formation occurring. Not only that, but because we have found them using our optical instrumentation, we know that they are very, very distant from us. They're 10 billion, 11 billion years into the past is when we're seeing these galaxies. And these are the types of galaxies that I studied exclusively in my thesis work, and we're continuing to study them at the University of Texas. They're very, very interesting. So I'll talk briefly for a few minutes about the work I did as a graduate student. I actually did my graduate work at Arizona State University in Tempe. And to find these galaxies, we have to, of course, go to telescopes, take images. So I traveled to a couple of telescopes. There's actually a picture of me there. That's the Cerro Tololo telescope. It has a mere 4 meters in diameter, so about twice as tall as I am. I'm almost 2 meters, I think. And it's actually in Chile. You may wonder, why do we go down to Chile? And that's because the mountains of Chile, they're actually the foothills of the Andes. It's one of the best observing sites in the world for astronomy. It's very high, it's very dry. That site and also Hawaii have two of the best sites, and that's why you see lots of telescopes in those two places. And it's, of course, fun to go to those two places. So we went there. I was actually there over New Year's, which was kind of fun. At midnight, everybody just stopped working and went out and had a party that I had to call back to my thesis advisor and say, hey, we're not going to be observing for 2 hours. He was not a very happy man, but there was not a lot I could do. But we took an image of a region of the sky, and we used a very narrow filter. So if you're familiar with cameras, you might be familiar with filters. But what you can do is you can slide in a piece of glass that says it only lets blue light through, or only lets red light through. So you can take one in the blue and one in the red, and if a galaxy appears brighter in one than the other, if it's brighter in the blue one, you say, oh, this galaxy is blue. It's brighter in the red one, you say, oh, it's red. Those are called broadband filters that let broad swaths of color through. You can make those filters very narrow to only let a very narrow range of color through, and that's what we've done. We wanted to only let this Lyman alpha line through, and we had to pick a wavelength for this filter, and we picked a wavelength such that if we saw galaxies in the image, we knew that they had a redshift number of 4.5, which is kind of a meaningless number to you, but what that means is if we see anything, we're seeing these galaxies as they were 1.5 billion years after the Big Bang. A long time since the Big Bang, but that's also 12 billion years into the past. And so we can look at galaxies there, look at galaxies here, and say, okay, what do they look like there? They've had 12 billion years to evolve into what we see here. Okay, so that's a long time ago. It's reasonable to expect that they might look a little bit different. So I'll give you a brief synopsis of what we found. Using these new images, we found 100 new Lyman alpha emitters, so that's our fancy word for these distant star-forming galaxies. 100 of them, which was, I don't know how many existed at that time that we knew of, maybe a few hundred, so it was a sizable chunk, a sizable addition onto what we knew. But just the fact that we found them is very cool, but to study them in more detail to see what's going on, we wanted to measure the color of those galaxies. Are they blue? Are they red? Are they forming stars? Are they not forming stars? So to do that, we actually needed to use Hubble Space Telescope imaging. Now you might say, well, you found them from the ground. Why can't you just use ground-based imaging? And that's because they're very, very faint. So they're very, very bright in this one emission line, in this Lyman alpha light. But they're very faint at all of their wavelengths. And so you can try and see them from the ground, but it's really, really hard. So we were smart, I'd like to think, and when we took these images from the ground, we took them over a region of the sky that already had Hubble Space Telescope imaging. It's very hard to get Hubble Space Telescope imaging. If you, this past year, 10 times more people applied for Hubble imaging than were actually able to get it. We called it an oversubscription of 10 to 1. It's incredibly competitive. It's just a side note. But we were lucky. It's already existed there. And here's what we found. These are galaxies. They don't look terribly exciting. Each row is one different galaxy. Each column is a different wavelength. So this row here, these are actually the images that we took from that telescope over there. And this little blob here is a galaxy, and we're seeing just its Lyman alpha light. This is just one emission line. That might not impress you, but it impresses me because that's one very narrow space of wavelength, and it's really, really bright for how far away it was. We imaged for about 5 hours. You basically leave the camera open for about 5 hours to collect as much light as you can. And we see these guys here. These images here are Hubble images. Now you see they're these little tiny specks. The reason why they're much smaller here is because the atmosphere, the turbulence in the atmosphere actually blurs out images. Another reason why we want space telescopes. The light, as it goes through the atmosphere, gets bounced around, and essentially if you have a little small galaxy, by the time you see it on the ground, it's kind of a bigger blob. But we know about that. That's okay. So I wasn't surprised when I saw these. I was just glad that we saw anything at all. And this is some infrared images, where some of them you see, some of them you don't see. So what did we learn about these galaxies? Well, we found that most of these galaxies appear very young. It looks like some of them just formed a few million years ago. So maybe there was a time in the universe with no galaxies, and the galaxies started turning on. And what's crazy is we know that that's not the case. We know that galaxies had to form before that because we can go look at stars in our own galaxy, and some of them are 13 billion years old. And so that tells us, well, galaxies must have formed pretty soon after the Big Bang. It just wasn't these galaxies. These galaxies are also not very massive. They weigh anywhere from about 0.1 to 1% the mass of the Milky Way. And that's interesting, but that's also okay because, again, they have 12 billion years to form more stars or combine together or whatever they do to turn into our Milky Way. And the most interesting thing we found is that most of these galaxies appear dusty. So I haven't talked about cosmic dust, but basically what happens is when stars, really massive stars, much more massive than our sun, they live their lives really fast, and at the end of their lives, they actually explode. But during their lives, they've been combining atoms in their core, and they've been making what we call metals, things like iron, silicon, carbon, oxygen, which of course we all know and love. And what happens is sometimes these atoms combine into particular big grains that we call dust grains. And so what happens with these dust grains is the star explodes, some dust forms, and the dust just kind of sits there in the galaxy. But when you image the galaxy, the dust actually makes the galaxy look redder than it otherwise would. And so that's how we can infer the presence of dust. And so dust, there are many, many incredibly boring papers on dust, and I won't get into too much about how it forms, but what's cool about it is that it tells us if you see dust in this galaxy, we know that stars have lived and stars have died. And so this galaxy did not just form. And we wanted to find the very first galaxies in the universe. We know that's not the case for these. They're pretty young. Like I said, some of them only a few million years old, but stars have lived and stars have died. So we've not yet found the first generation of star formation. And that's really what I want to find. So we need to go to greater distances then. This Lyman alpha technique is not going to cut it for us. So, okay, let's go to greater distances. The problem is that now, once you go far enough away, so before we were at a redshift of 4.5, now we want to go to redshift of 6, redshift of 7, find these first galaxies. Essentially, all the light from these galaxies is now shifted into the infrared. So you can't see it with your eyes. You can see it from the ground, but the sky is very bright. It's very difficult. So you really can't actually see it from the ground. So we need an infrared camera in space. I mentioned there's the Spitzer Space Telescope that's already up there, and it's still working. It's great, but its mirror is only 80 centimeters, so it's about this big. Great for a lot of things, not great for finding really distant galaxies. The Hubble mirror is 2.4 meters, a little bit taller than I am, and essentially that makes a huge difference in your ability to find these distant galaxies. And I'll talk a little bit in a minute about a new telescope we're building that's going to have a mirror 6.5 meters in diameter, and that's going to be great. So we need an infrared camera in space. We need it on Hubble. The Spitzer telescope is not going to cut it. Hubble had an infrared camera, but it did not work very well. It had a lot of problems. So luckily, we managed to convince NASA to send one more space shuttle mission to the Hubble Space Telescope. You may have seen this on TV. This happened in May of 2009. And one of the things they did is they not only fixed it up to last hopefully another 10 years at least, they installed this camera called Wide Field Camera 3, or in our astronomy lingo, WISC-3, and it's an infrared sensitive camera. It can also take pictures in the optical, so you can see with your eyes, but it's great in the infrared. So here's a picture of Hubble, actually taken from astronauts in the space shuttle. You can see the Earth below. And here's actually a picture of some astronauts installing the camera right here. So this was taken on this mission. It's now been over 2 years. It seems like just yesterday. But this camera has been fantastic. So I'll talk for just a few minutes about one of the main results that we've obtained from data from this camera looking for these first galaxies. What's great is this topic, looking for the first galaxies, is kind of the number one science driver. So the first thing we were able to get this camera to do was to stare at one spot in the sky for like 100 hours. It's an incredibly long period of time for Hubble, but if you want to see these faint, tiny galaxies, you've got to stare for a long time. This field, not originally, is known as the Hubble Ultra Deep Field. There was a Hubble Deep Field, this one's deeper, so it's the Ultra Deep Field. This had actually already been imaged in optical light, like you can see with your eyes. That's actually in the background here. I'll show that again. So here's the Hubble Ultra Deep Field in the optical. This was taken, I think, in 2006. Every little speck you see here is a galaxy, which is amazing. But what we know about these galaxies, because we see them in the optical, they are at a redshift of less than about 6. So we're seeing light from them about, they can't have been from before 1 billion years from the Big Bang. So we can't see anything further than that in the optical. So that's cool. This guy here actually might be a star, but for the most part you see galaxies. And you can look this up online. You can Google Hubble Ultra Deep Field. You see this. That's a galaxy. That's a cool looking galaxy. And you can actually, there's some websites where you can zoom in and pan around. It's great. But this isn't going to cut it for what we want to do to find these most distant ones. So this here is an infrared image. The infrared camera is a little bit smaller, so we don't cover the whole thing. But now we're seeing things that we couldn't see before. Anything you don't see in this image, and you do see in this image, is a candidate distant galaxy. We call them candidate because we're not quite sure. There are methods we have for confirming their distances, but until we do that, we're not quite sure. But it's really cool. So you can just literally load them up on your computer, blink them back and forth. You can pick them out by eye. It's not actually the way we do things, but you can. So what we do is we use some software, unoriginally called Source Extractor, because it looks in the images, finds sources, and extracts them. It's optimized for finding these distant faint galaxies. It's great. That's what we want to do. So it looks in this image, measures all the galaxies here, looks at this image, measures all the galaxies here, and then using our computer, we say, okay, tell me which galaxies are here and not here. And we have found about 100 of them in this image so far. And here are a few examples here. The top one, that's actually the most distant one. It has a redshift of 8.6. You can see in the optical image on the left, you don't see it. And in the near-infrared image on the right, you see this little green dot. That's that galaxy. This one's pretty cool. You almost barely see it here, but not really. And it's this cool string-like structure here. Here's another one. You see nothing here. You see this little tiny speck here. So it's quite easy once you understand why this works to actually go take these data and go find these galaxies. And because it's quite easy, this field is incredibly competitive. There are 5 or 6 groups around the world trying to do this all at the same time. So interesting and fun and sometimes a little bit stressful. So here's an image I made. Actually, so I said we found over 100 now. We wrote one paper on kind of the first set of results where we found 35. So each of those little squares is a galaxy in this image. The upper left is the lowest redshift one we found, which was that redshift of 6.3, which is still incredibly distant. And then marching around to the right, they get progressively further away until that little green dot is right there, the redshift of 8.6. These little squares here show you where we found the galaxies around the image. So the redshift range that we found these at, from a redshift of about 6 to a redshift of about 8, corresponds to about 600 to 800 million years after the Big Bang. So now we're almost a billion years further back in time than what I studied in my thesis work. So what do they look like? Is there anything new? And the most interesting question we want to ask is, have we found the first galaxies? Have we found the first stars to form in the universe? And I'll tell you the answer is no right now. And here's why. So we know that after the universe formed, again, we only had hydrogen and helium. Those first stars to form out of hydrogen and helium would have been incredibly hot. And if you get very, very hot, you get blue. People commonly think that things that are red are hot. Blue hot is much, much hotter than red hot. Okay, you can do that. You can heat something, you'll see it get red and kind of white and blue. So these stars would appear very blue. And so because we know that, that's an easy question. Well, let's look at our galaxies. Are they blue? How blue are they? Are they blue enough? And so we did that, and it turns out they are very blue, but they are not blue enough to basically host these first stars to form in the universe. And the way we did that is we looked at nearby galaxies, which we understand very well. We said, okay, this particular galaxy with the name NGC 1705, not a very interesting name, is the bluest nearby galaxy. We studied this galaxy in great detail. We know that it has normal stars. These stars were not the first ones to form in the universe. They're typical run-of-the-mill stars. And the galaxies we see in the distant universe have colors very similar to this galaxy, NGC 1705. And so that's one way of saying, well, these galaxies are surely interesting, and this NGC 1705 is interesting, but they're not the first galaxies to form in the universe. So now we're 600 million years after the Big Bang. We still haven't found the first galaxies. So we're kind of pinning down the time when these galaxies could have formed. And I'll just mention one thing. In addition to the colors, we wanted to see how massive were these first galaxies. And again, they're very, very tiny. They're about 1% as massive as the Milky Way. So actually similar to those redshift 4.5 line alpha galaxies. But they're very small. They're very blue. They're just not quite blue enough. So I kind of dubbed them baby galaxies, but they're not yet infant galaxies. We have to keep looking to find these first galaxies to form the universe. So how can we do that? We've kind of maxed out Hubble, although don't tell that to the people who decide because we're asking for more data to do more and more things. But we're never going to find the first galaxies with Hubble, which is unfortunate. What is not unfortunate is that we have a plan to do this. This slide needs to be updated. It's now late 2018. NASA will be launching something called the James Webb Space Telescope. I'm actually just curious. You could raise your hand. How many here have heard of James Webb Space Telescope, or JWST? Okay, a few. Pretty good. All right. So a lot of work eventually on this will be done in Houston. So you can familiarize yourself with this. So the mirror of this telescope is 6.5 meters in diameter. Again, Hubble was 2.4 meters, so a little bit bigger than this. This guy is going to be almost 3 times that. And the light gathering power, which is a way of saying how deep can you see, goes as the mirror diameter squared. So if it's 3 times bigger, it's going to be able to detect things almost 10 times fainter, which is fantastic. Or, well, 7 if you do the numbers right. What's also interesting about the James Webb Space Telescope is that it's optimized for the infrared. It will be able to take optical images, but not all that well. And that's because this telescope is basically a distant galaxy finder. We want to find these distant galaxies. We know we need to look in the infrared. So let's build a telescope that's optimized for the infrared. And we think that we should be able to get down to about 300 million years after the Big Bang. So if the first galaxies form after that, we will see them with this telescope, the James Webb Space Telescope. It's very exciting. It almost got canceled a few months ago. Congress, the House tried to cancel it. The Senate did not, and they managed to keep it in the budget, which is fantastic. And now I don't think it will get canceled. They have a good plan. There were some budget overruns and other problems. Maybe you can talk about one of your more political seminars. But it's going to happen in now a little over 6 years, and it will be incredibly exciting. And me and others here at UT will be working on the data, and we'll have to come back to tell you about it. So for just the last few minutes, I'm going to talk about dark energy. This is actually the topic I was asked to come and speak on, but I'm far from an expert in it, so I've kind of delayed it till the end. So far in this talk, I've been talking about a type of matter we call baryonic matter, and that's matter that's made up of atoms. When we go out and look at the universe, this accounts for only 4% of the total energy density in the universe. That's insane. Everything you see, everything you know, is only 4% of what exists. And we call it energy density because, as Einstein here would tell you, the energy equals mass times the speed of light squared. So you can convert between energy and mass. And we won't get too much into that. But essentially, we know how much energy there should be in the universe. Only 4% is in matter. Okay? There's another 20% or so in something called dark matter, which we also don't know a lot about. And as it turns out, the vast majority, 74%, actually we think about 72%, is in something called dark energy, which we also know almost nothing about. Okay, so how do we even know dark energy exists? We didn't just make this up. I'm not trying to pull a fast one on you guys. So I'll talk about exploding stars again very, very quickly. The biggest piece of observational evidence for dark energy has to do with these typical type of exploding stars called type 1a supernovae. So I said that a supernova is a really massive star that explodes, which is true. Those are type 2 supernovae. Type 1 supernovae are actually quite different. There's something called a white dwarf, which is actually the eventual end, what will eventually happen to our sun once it lives its life. It will kind of peacefully blow off its outer layers, and the core of our sun will just sit there, this little white hot ball about the size of the Earth. Every low mass star in the universe eventually ends as a white dwarf. So there are lots of these white dwarfs out there. If a white dwarf happens to be close by to another star, this is not an actual image. We cannot see this like this. This is an artist rendering. But this is what we think happens. It gets close enough, and through gravity, it actually sucks gas out of the atmosphere of this nearby star. It's crazy. It's very interesting. And what happens is, once enough mass gets onto this white dwarf, the center of the white dwarf gets so hot and so dense that it essentially explodes. All the hydrogen or all whatever's in there, helium or carbon, fuses together and blows the star apart in something we also call a supernova. It's very different than the type 2 supernova. But what's very great about this type is that when these type 1a supernovae explode, they all explode at the same mass. So they get enough mass on their outside until they are 1.4 times the mass of the sun. So it's called the Chandrasekhar mass. And only once you get to that mass do you get that nuclear reaction in the center that blows the star apart. So as you might imagine, these things ought to all look more or less the same. And it turns out they do. These all explode the same way, so they're all the same brightness. And that is great, because then we can use them to not only, we can see them across the universe, essentially, but we can also find out how far away they are. So because they all explode at the same mass, they all have intrinsically the same brightness. So just from measuring how bright they appear to our eye, or really our telescope, we can then tell how far away they are. And the greatest way to imagine this is if you took, say, 10 60-watt light bulbs, so all the light bulbs look the same once they're close to you, and put them farther and farther away, just from how bright they appear to your eye, you would be able to say, this one is this far away, that one is that far away. And we're doing the exact same thing with these type 1a supernovae. So just by looking at them and measuring how bright they appear, we can say, we think they're this far away. Then we go and take a spectrum of them, and we look for these spectral lines like H alpha or Lyman alpha, and we say, okay, this is what their redshift is. This is how far their spectrum has been redshifted due to the expansion of the universe, and we can see if those two numbers match. And it's somewhat complicated to understand how you would compare those two numbers, but essentially, go to the next slide here. I'll just show it here. Depending on what the universe does, we can make predictions for how the brightness of a galaxy or brightness of a supernova and its redshift would match. If the universe was as we thought it was before 1998, which was regular matter and dark matter and nothing, all the supernovae would have lied along this line in this plot. So this is essentially everything's at zero when the predicted brightness matches the observed brightness as a function of redshift on this axis here. So we're getting farther and farther away. Okay? When things are above the line, they're actually fainter than we predicted. When they're below the line, they're brighter than we predicted. Okay? When we look out very close, redshift less than 0.1, so very close by, things kind of lie on this line. As you go to more and more distant galaxies, they tend to lie above the line. What that means is these supernovae are fainter than we thought they should be. And the only way to explain that is that the expansion of the universe was actually accelerated. And that was the conclusion that two independent studies made in 1998, and they actually just won the Nobel Prize a few months ago in physics for this discovery. And essentially what's happening here, we had thought that the universe was something like this, where there's a big bang, it just expands and expands forever. There was a possibility that it was like this. Maybe it expands for a while, and then it comes back. But it turns out our universe is actually like this. It starts expanding normally, and then there becomes an epoch in the universe where this dark energy takes over and accelerates it faster and faster. And so this is kind of an abbreviated history of the universe. In this picture here, The Big Bang happens here. I'm sure we'll have questions about that. We don't know what caused it. I can tell you that now. The Big Bang happens here. The universe starts to expand. Okay, at the very beginning, it's the matter-dominated regime. The universe is so small that it's completely dominated by matter. Dark energy does not play a role. But once the universe expands enough, the density of matter gets low enough that now this thing called dark energy begins to take over, and the expansion of the universe just begins to take off like that. Okay? So, I'll finish by talking about one aspect of dark energy. Not only do we not know what it is, I'll put that out there, we have no idea what it is. It's great that they won the Nobel Prize, but I don't know if there's ever been another Nobel Prize awarded for something we have no idea what it is. We've measured the effect, we know it's there, but we have no idea what it is. Even more interesting than that, we think that dark energy does not evolve with time. So it's just as strong here as it is here. And we've tried to measure this, and the measurements we come up with are kind of consistent with it doesn't evolve, but there are some decently sized uncertainties. So we really need to look into that. Does it evolve with time? Because that has very important impacts on the eventual fate of our universe. Okay? So this is something that we're trying to do with HETEC. So in the introduction, Mike mentioned HETEC. HETEC stands for the Hobby-Eberly Telescope Dark Energy Experiment. You might be aware that out at McDonald Observatory in West Texas, we have an almost 10-meter telescope, one of the largest telescopes in the world, called the Hobby-Eberly Telescope. Here's an image of the telescope here. You can see it around me there. Very interesting looking telescope. And we designed this dark energy experiment to probe, is dark energy evolving? And this is a project that's led by astronomers at UT. We're collaborating with Texas A&M. They're actually helping us build the instrument, Penn State, and some other institutions in Europe. And HETEC is going to use an instrument that's called VIRUS. It stands for Visible Integral Field Replicable Unit Spectrograph, which doesn't really mean anything. It does mean something. Basically, we've designed one spectrograph to go search for galaxies, and they're going to replicate it 200 times in an assembly line process. And it turns out that as long as your instrument can be built with 200 of one thing, it's incredibly cheap. It's much, much cheaper than the way instruments have been built. And so we're going to take 200 of these spectrographs, strap them on this telescope, and we're going to actually use them to look for these Lyman alpha galaxies that I'm very familiar with, I talked about earlier, at a redshift of about 2 to 3. So that may seem now pedestrian to you, because I said we need to go to redshift 7 and 10 to find the first galaxies. Well, this is a different topic here. We just want to trace dark energy. And redshift 2 to 3 is a great place to do that. And what we're going to do is we're going to find 1 million of these Lyman alpha galaxies. So if you remember I said in my thesis I found 100 and I was ecstatic. I found 100. We're going to find 1 million. Actually, 4 years ago I went to a meeting and I saw a poster advertising this instrument and they said 1 million and I thought it was a typo. So I don't think I've actually admitted that to anybody here at UT. And what we're going to do is we're going to study how do these galaxies cluster together. Are they kind of randomly distributed? Is there some length where they tend to cluster around? And by comparing that number and looking at similar clustering experiments at both lower redshift and a higher redshift, we can actually trace that expansion of the universe. So we can go back and look at, look at this curve here and see, does it go out like that? Does it fan a little bit closer? And using that, we can actually tell if dark energy stays constant as time goes on or if it evolves. So here's an image of what the HET will look like. Now this is an artist rendering where we've taken out the dome, just so you can see inside. Each of these little things here are spectrographs. We're going to mount them on the side of the telescope here, and then these little green things are a bunch of fibers that are going up to the top of the telescope, and so the light comes in from a galaxy, hits the telescope, goes up here, goes in one of the fiber comes down here, and then we make a spectrum. And then we look for this Lyman alpha spectrum line, and we say, hey, there's an LAE, a Lyman alpha emitter, I know right where it is. And our main survey is actually probing an area around the Big Dipper. That's what's shown up here. It's kind of hard to make out the Big Dipper, but that little shaded in region is what we're going to do. And we're surveying a huge area of the sky, much, much bigger than most surveys, to look for these galaxies. That's how we're going to get so many. So we're currently assembling these 200 spectrographs now, both here and at Texas A&M University. And I've talked about the technique and how it's cheap. So our plan is to hopefully have some ready to begin installation by this fall, and we're hoping to begin our main survey in the spring of 2013. There's a great public outreach group in our astronomy department, and they've created this website, hetec.org, so you can go there, and there are videos, interviews with astronomers, videos about dark energy. Everything you ever wanted to know about dark energy that I was not able to explain to you exists on that website. And once we actually start doing the experiment, we'll be posting the results there as well. And so I'll just end with saying that the future is very exciting for astronomy. We have learned a lot, obviously, not only in the the 6 or 7 years that I've been doing it, but in the hundreds of years previous that people have been learning. But it's amazing to me that we still don't know what dark energy is, what dark matter is, and that's 95% of the universe. We still don't know what it is. We don't know when the first galaxies formed. And one of the ways to study these things is to build better and more advanced experiments. As time goes on, we get better and better technology. We can do more interesting things. And the next 10 years should really give us our first glimpse into the first galaxies forming in the universe. I've already talked about the James Webb Space Telescope. There's a website here, jwst.nasa.gov. It has lots of information on that. And then there's something I haven't mentioned called the Giant Magellan Telescope, which you can learn about at gnco.org. That's actually this image in the background. This is a telescope that the University of Texas is a partner in, one of 10 institutions, and it's a 25-meter telescope. So I mentioned Hubble is 2.4, JWST is about 3 times that. This is 25 meters, okay? It is insanely big. We're building it, unsurprisingly, in the mountains of Chile, and it has 7 of these mirrors here. Each of these mirrors is 8 meters in diameter. To give you a scale here, here's a semi-truck here that shows you how big this is going to be. And if everything goes as is currently planned, this will be up and operating by the end of 2019 or the beginning of 2020. And this is just going to be fantastic. We will definitely need the James Webb Space Telescope in space to find those first galaxies, but if we want to follow them up with a spectrum to learn more about them, this is going to be the guy to do it. And I hope to be here to be using this instrument to do that. So I think that's it. So I'm ready to take any questions about anything I've talked about. Thank you.
Yes. Let's give him a big hand. Michael, do you want to ask a question?
Just answer any part of the question you want. But with these, I'm concerned because I'm a minister, and in the Bible it says the universe is eternal. God is eternal. It's the same word actually in the Bible for God, universe, and eternal. So you're coming up at the end of the universe. You will see the end of the universe someday.
Well, we're looking actually for the beginning of the universe.
All right, but still, that's the boundary. And what I want to know is, do you think there are other universes on the other side of that?
Right.
And I'm just concerned about the eternal nature of humans. We think we're eternal. And if there's an end to the universe, that might belie that spiritually.
Hey, that's a very good question. So to address your second point, what's great about dark energy in the accelerating universe means our universe won't end. There were scenarios where if there was no dark energy and there was a little bit more matter, the universe would kind of collapse. That's not going to happen. It's just going to expand forever. So we know that very well now. In terms of how did at the beginning of the universe, there are a number of theorists, because we can observe this, who sit around and think of ways, how would something have happened to form our universe? How did this happen? And we have no idea. We don't know what existed before the universe. We don't know if the universe is existing in some other bigger thing. There are a number of interesting theories, and one of the ones that I don't have an image to show it. There's a theory called the bubble universe theory, where there's some other medium that our universe exists in, and there are other universes that are kind of popping off in every direction, and we just happen to live in one. So if you Google bubble universe, you can see a really great graphic about how that happens. And if that's the case, some people also call that the multiverse theory. If that's the case, then maybe we're just one small part of the overall universe. We're just whatever we can see is one small part of that. But the observations we're making come the closest to looking at that, but we're still so far from ever hitting really close to the Big Bang. I'm actually skeptical about whether we'll ever see the first stars to form the universe because they happened so long ago. I don't know how big a telescope you would need in space, but it's much, much bigger than we'll be able to fund in the next few hundred years, I think.
We have a question right here.
Yeah, I wonder what are the Chinese doing in this area, and is there any collaboration between us and the Chinese or the Russians?
No, there's absolute collaboration. Actually, my thesis work, there were a few Chinese astronomers I collaborated with, and I still do. I don't know everything they're doing. I know one project. There's a professor actually at Texas A&M, Li-Fan Wang, who's Chinese, and he's working with the Chinese government to build telescopes in Antarctica, which you might think would be a strange place to build a telescope. But as it turns out, I mentioned we build them in Chile because it's both high and it's dry. If you go to the tallest place in Antarctica, it's, I think, even taller than the site that we're building telescopes in Chile, and it's incredibly dry. The atmosphere is dry, and because of the way the atmosphere of the Earth is distributed, if you're at 15,000 feet in Antarctica, you have less air above you than if you're at 15,000 feet in Hawaii or in Chile. So that's a wonderful place to build it. It's incredibly hard to build there because you can only get in and out, I think, 4 or 5 months out of the year. So essentially you need to get people willing to winter over in Antarctica, which they do. But right now there are a few 1-meter telescopes, so this big there. They want to build first a 4-meter telescope, and then go from there and see if it works. And that, depending on how it goes, could end up being cheaper than space. You can't do everything that we can do in space, but it's better than what you can do from some of the other mountains.
Unfortunately, our media team is signaling that we're out of time, but I'm wondering if you might be available to answer a few questions,
Sure, yeah.
say a few minutes. Thank you so much for a wonderful, inspiring presentation.
Okay.